Am I audible to you? Okay, that's great. Now, today we will actually, I think, congestion control and traffic shaping is remaining, and that is covered by Sheetal madam. She is going to complete that part. So we are going to start a new topic. Okay, that is chapter 4 of Tenant Bump. That is medium access control sublayer, MAC sublayer. Okay, so here, what is the assumption here? That it is now we have a common medium, right? That means we are sharing a cable, or rather we can say we are sharing the channel like it is a wireless. Suppose it is a wireless, right? Or suppose it is a wired and bus topology. So it is possible that we all the machines are sharing the same cable. Right now we are working. Now we are not working on the network layer, right? Now we are working on the LAN, that is we are working on the lower layer than the network layer, right? So here we are now having physical connection between machines. It is not like it is not like there are end-to-end connections and the intermediate machines are there. Right now what we are discussing, that how actually a packet will pass through from one machine to another machine which are actually physically connected. Those two machines can be the that end-to-end machines, or they can be one is source and other is a other is a intermediate one which is supposed to pass to further one. Right now what we are discussing, that how two machines which are actually connected, physically connected, and they are going to deal with. And here whatever the physical connection is, that is shared by many. Okay, so here we are working with the topologies, which suppose it is a bus topology, then same wire we will have in that topology. What will happen? We will have there is a common wire, and all the machines are physically connected with that wire. They are tapped together. So this wire is shared, right? That wire is shared. So here, this is a medium, this is a medium, right? It can be wired or wireless. Suppose it is bus topology and this is a wired medium, then this is shared by many computers, right? So now whenever it is shared, right, this, if this wants to communicate with this, it will use this one, and if this wants to communicate with this, then also it is going to use the same one, or if this wants to communicate with this, then also it is going to use the same one. So when all the machines are using the same medium, they need to have policies to access them, right? Who will access first? And who will access when? How much the one will access? Those are the policies are required, right? And that is who will access the medium, that has to be controlled, and that is what is done by MAC layer, medium access control. Okay. So here you can understand this one. This is not difficult to understand, right? Suppose you can imagine the classroom in which we are together, right? Generally when you come here physically, we sit in the classroom, right? So in that there is a common medium, wireless medium, right? All of we will speak and use that wireless medium, that air, that atmosphere to pass our signals. Like here we are using bus, here we are using this copper cable. In that way we are using air. So we are having, so we all are the source or the destinations at that time. We are all are the terminals at that time, and at that, and the medium, that wireless medium or air is the medium which is to be shared among us, right? Then whenever I am speaking and all of you will start speaking, right? So that situation in that if all of us will start speaking together, right? So then definitely no one is going to get anything, right? And hence what is required in that scenario, that who will speak first, right? So and whose turn will be when, how much a one will use the medium, those are the policies required, and that is what will be done by MAC layer. So are you clear with the idea that what is MAC layer? Are you clear with the idea what is MAC layer? Okay, that's great. Now what we are doing here, where the MAC layer exists, So, because we are dealing with physical connection between machines, right now I'm not interested whether this is source and whether this is destination or not, whether it is an intermediate machine, whether this is a router and this is the destination. This is whenever we have source, router, destination, right? So, possibly this is the connection, this is the connection, or possibly we are having source to destination direct connection. We are not interested in that right now, right? So what I'm interested in, that when I communicate with my next machine physically, which is physically connected with my network, and if I'm sharing the medium, how and when I should get the turn, so that what should not happen. If I'm not, see, if I'm not taking care of this turn by turn, or I'm not taking, so what are the problems that can occur? Why we need medium access control? We discussed already, so you should have that idea in your mind why we need medium access control. Congestion, no, not congestion, genuine congestion is what, that so much traffic will be there at the router, so the router will be out of the buffer memory, and maybe that you want to say, you don't want to say congestion. Congestion is what, then load is more than that it can be handled. Right now, and it is possible that only one packet this machine has to send, and then one packet next machine has to send, possible. But if they send together, then what will happen? Only one packet is required to be sent by this data loss. So what we will call it? Collision. Collision. We will call it as collision. Understood? It is not congestion. Congestion is what, when we have a lot of load to handle. And what is collision? No need to be sorry, but you should be able to identify one more term we are going to learn is contention. Contention, congestion, and collision are all three different terms, and you must be able to understand. So, are you clear with what is collision? Collision is not delayed transmission. Collision is what? What is collision? What do you understand? Delayed transmission. See, delayed transmission will not take. See, Harsh. See, delayed transmission. When delayed transmission, suppose like we are in the classroom, right, Harsh? And I speak, and okay. So you okay, so collision will not. Yes, in congestion, delayed transmission will happen. That is true. That is fine. So you are clear with collision and congestion, Harsh? Okay, that's great. Um, yes, when more than one packet simultaneously send, when two entities want to transmit data at the same time. Right. So now let me know. Let me tell you that what exactly happens. Suppose I want to send five. I suppose I want to send bit. Suppose I'm using this copper cable, right? And I want to send bit one, right? Bit one, that is 5 volt. I will send, right? And what will happen here, suppose this also wants to send something, suppose it wants to send 0, and it uses -5 for -5 volt for -5 volt for sending 0. Now this uses copper cable for sending +5 volt, so on this line there are +5 volt. So how, suppose this machine wants to see, now we have the common line, and I am having multiple machines here, right? Now this is a shared medium. Now let's see, these basic concepts are required to be clear, and then I will start the actual ones, right? This is not the actual concept, but this is required to be clear. So okay, now suppose first of all let us understand that A wants to communicate with C. Okay, so this sends, suppose bit 1 it wants to transmit, so what it will send? +5 volt it will send. Where it will send? On this line. This is a copper cable, so here +5 volt will be available. Now here this machine is X and this machine is Y. Who will listen this 5? Can X and Y listen this 5 volt? Can they sense +5, I mean voltage is here? Who will get the information? Who will get the information? Which machine will get the information? This +5 volt, who can sense? All. Yes, because it's a shared medium, all can hear that, right? All can hear that, right? That is what the shared medium is, right? That is very common. Like in our classroom, if someone speaks, then everyone can listen that, right? Whether to process or not, or whether to accept or not, that is a separate thing. right? But everyone can listen for sure, right? Then they will think, okay, this is the doubt, but I don't have that doubt, so I will not uh, listen what madam says because I don't have that doubt. So I didn't process. Or yes, I have the same doubt, I'm going to understand and I'm going to solve the same doubt. So that is I processed it, right? So whether to process or not, that is a separate thing, right? And whether we should process or not as a machine here in the medium, that is another ethical thing, right? But whether I can do or not, yes, I can do, right? So every machine can listen, okay? And ethically, we are assuming that all users are ethical and they are not going to listen, so that this too will discard the data. It will not listen, will not give efforts to listen this channel because it is not meant for them, and this will listen the channel throughout, and it will listen the one. How? For that we are going to learn this entire process, so do not worry about it, okay? So that is fine. Now what happened, now this was sending 5, at the same time this wants to send 0, okay? So now can you tell me what will be the voltage on this line? What will be the voltage on this line? This wants 5, this wants -5. What will be the voltage on the line? 0. Yes. So voltage was 0. So this is known as collision. What is collision? That my data altered. My data was what? +1. Now what I'm receiving is 0. So my data altered, right? I'm getting 0 volt. So my energy changed, right? And possibly this will not come to know whether what was transmitted, right? The C will not come to know whether, it will understand if it is +5 volt, then 1. But what is the meaning of 0? Whether whether A is transmitting or not. No one is transmitting, then also the voltage is 0. And if this is transmitting and someone is colliding with it, then also the voltage is 0, right? And suppose this also transmits zeros, then can you tell me what will be the line voltage now? What will be the line voltage now? This transmits 0, this transmits 0, and this transmits 1. What will be the line voltage now? +5, -5, -5. +5, -5, -5. What will be the line voltage? +5, -5, -5. What will be the line voltage? -5. The line voltage will be -5. So what this will detect? Okay, A is transmitted 0. So this is known as collision. Data altered. Data lost. Okay. So now, okay, so this is what is all about collision, right? Okay, now can you tell me, will A come to know about collision? Will A come to know about the collision? How? Not acknowledgement. I'm not asking about acknowledgement. Yes, it is a shared medium. Yes, Janelle, it is a shared medium. That's why, see, as 1 was transmitted, as +5 was transmitted, X, Y, C were able to listen. At the same time, A was also able to listen it, na? Right? Exactly true. So here -5 volt is there on the line. So that also can be sensed by A. So he will understand, okay, I transmitted +5, but I'm receiving -5. That means collision has happened. Okay, so this is what is known as collision detection. How to detect? By listening the channel. So these are the words that I'm going to speak now onwards, right? So you should be able to understand what is the meaning of them. Okay, so listening the channel, if I transmit it, so I put 5 volt here, I placed +5 volt here, and then I was listening the channel. If I was getting +5, then I understood, okay, it is my data only, no collision has happened. But okay, now I'm receiving -5. That means someone started transmission and I lost my data. I will detect the collision. Is it clear or not? Are you clear with that? A can detect the collision by listening the channel? Great, great, great. So now, so this was the basics that will be needed. Now let us start with the actual topics. Okay. So now what is the, where we are actually working here in the Mac? Channel allocation. Who will get access of channel allocated to whom, right? So there are two methodology for channel allocation. One is static, another is dynamic. Static is what? That initially I will allocate, suppose I have 4 users, so I'm going to allocate a channel, I'm going to allocate chances to them, right? And statically, initially, Okay, I will not take care about the load or anything. I will just simply allocate the channel initially. So that is what static allocation is. So what are the ways to allocate channels statically? So it is FDM and TDM. Do you know FDM? What is FDM? What is FDM? It may also have happen that after receive data of a other data is transmitted, then also it may also happen that after received data. So that is fine. See, Priyank, if see this is how we will take care of it, right? That whether it is received or not, for how much time we have to sense, that everything we are going to take care of it. But it is possible that if it is, even if it is received but the sensing time of A is not over yet, then it may detect it wrong. That can happen, right? So this is limit. We are going to work with the limitations only, right? So that is fine, but it is not going to be as drastic as you are thinking, because we have to deal with the policies. We have not discussed any policy yet. I am just discussing the terminology. When I say listening the channel, what it means, or how by listening the channel it will come to know. That some basic concepts I am just speaking about. I have not discussed yet any policy, right? I'm just discussing the terminologies. Okay, so that when I say that collision will happen, so you should not get confusion, you should not get confused with contention or congestion. Contention I yet have to take. Okay, and you should not get confused with when I say collision can be heard. What is the meaning of collision can be heard, right? So now onwards I will use those terminologies. So yet I have not discussed any policy. Okay, so now I'm discussing any other doubt in case anyone is having, then I can start the new one. Otherwise, this next topics will see what I've discussed. I've just discussed some terminology, and so that you should be clear with when I speak directly them. So that terminology you should not be confused with. Any doubt? Anyone? Please ask. Okay, so I'm assuming right now no one is having doubt. Okay, so what I'm telling you is, suppose I have now does anyone know about FDM? FDM? Yes or no? According to that I can start. That's why I'm asking. Do you have idea about FDM? No. Okay. Okay. So FDM is frequency. Yes, it is frequency division multiplexing. Okay. So see here, a frequency division multiplexing. It is frequency division multiplexing. From the name itself you can understand what we are going to see. What I have a channel that I have to share among users initially. Okay, so so suppose I have bandwidth say 0 to I have 12 kilohertz in my channel. I can transmit using frequency of I can use electromagnetic signal of zero frequency to I can use signal up to 12 kilohertz, right? If I have my signal has frequency say 11 kilohertz, it can be carried by my channel. That is what the meaning is, right? So so now I have suppose three users with whom I have to share this channel. Okay, so what are the chances I have? Okay, so um, what we can do is that I can divide this frequency, that 0 to 4 kilohertz, if you will be given to user 1, 4 to of course 4.1, whatever you consider, 4 to 8, I'm just writing it for rough estimation, not exact one. You can write 4.1, okay, or you can write 3.99, whatever you want to keep here, that is okay. And 8 to 12 to third one. Okay, so what is the meaning? Suppose I'm a user 1, then I can use signals or I can use bandwidth from 0 to 4 kilohertz, right? Or I can use signals from 0 to 4 kilohertz electromagnetic wave I can use to transmit my data. Same way, this user 2 can use these frequencies and user 3 can use these frequencies. Now what will happen at the receiver end? So now suppose three users are there. All three are having data at the same time. So so user 1 will send in this band, user 2 will send in this band, and user 3 will send in this band. So all three are transmitting together. They are in the channel together. In the same channel, they are transmitted together. Okay, but at the so what will happen? Three channels and all three signals are transmitted together here. So three different frequencies are carried by this channel. Okay, and on one end there are three users, and all three are sending simultaneously here. But on the other end, what will happen? This three will be given to three different antennas. One antenna will just detect the signal from 0 to 4, another will detect from 4 to 8, and third will detect from 8 to 12. So see what will happen. This antenna is going to reject all the signals above 4 kilohertz. This is going to reject this band and this is going to reject these two bands. So can I say here I can get three separate signals? Yes or no? So this is what is FDM. So what happened? All the users, all the users used the channel at the same time. Can I say all the users were sending at the same time? But what was shared? The bandwidth was shared. What was shared? The frequency was shared, and that's why it is known as frequency division multiplexing. Multiplexing was done, but um, it was done in terms of frequency. Second possibility is what is TDM. This is so initially this was static because initially I allocated. Now suppose user 1 and 3 has data but 4 is not having data, so this will be unused one. This will be unused one. Okay, and now suppose user 4 comes. So suppose fourth user comes and it has data, and currently user 0 and 3 has data. This band is unused. Still I cannot accommodate fourth user. Why I cannot accommodate? Because already I have allocated my available bandwidth, though this is not useful, but it is statically allocated to user 1, and hence I cannot give it to user 4. Are you getting the point? So though it is unused, because it is already allocated, I cannot allocate to anyone, and I have to deny to the new user. Okay. Because that is what is assumed, that every user needs at least 4 kilohertz as a requirement. That is what is assumed here. That below less than 4 kilohertz is not acceptable by any user. So we have to deny the fourth user. Is it clear to you? What is why it is static and what is frequency division multiplexing? Is it clear to you? FDM is clear? Should I repeat anything? In case needed, let me know that so that I can repeat. Now next is TDM. Can you tell me what it will be? Time division multiplexing. Can you tell me how it will be different than this? Can you think of? Then can you use your logic and tell me? What can be TDM? Not response time. What is response? We have a channel, right? We have a channel. We have to share among users. So let us keep three users. Let us keep the same channel 0 to 12 kilohertz. Hold wait. First 2 second transmit, next 2 second. Yes, first 2 second A transmit, next 2 second B transmit. True. Assign some portion of time of transmission. True. See, wavelength, generally, wavelength, if you will go with wavelength, is nothing but F is equal to C by lambda. So if you are dividing frequency, actually you are dividing wavelength, right? So C is a constant. So FDM, modified version of FDM is wavelength division multiplexing, right? So right now let us not go in that detail. We will go to that in case needed. But right now it is not related to TDM. Is it clear to you? So wavelength will not come into picture right now. It will come soon, but not now. It will be related with FDM, not with TDM. Okay, so that is yes, channel. You are correct here that so turn by turn, one by one. Like who will send first? So first 2 second will be given to user 1, then 2 second to user 2, next 2 second to user 3, next 2 second to user 1 again, 1, 2, 3, then 1, 2, 3. So we are allocating time. So what about bandwidth? User 1, when user 1 has a chance, how much bandwidth it can utilize? Full bandwidth it can utilize. True. So that is how it is different from FDM, that in FDM all the user can send at the same time but not full bandwidth, and in TDM one at a time but full bandwidth, right? So that is what is TDM. Okay, now let us go with some more. See, we are not interested much in static allocation. We should have idea, but we want to go with dynamic channel allocation, right? So before we go there, what is the problem with this? What is the problem with FDM, TDM? Why we are not going to take this static allocation? One is that as user increases, not low bandwidth, fine, but yes, you can say low bandwidth if it is a frequency division multiplexing. Then if number of users are more, you have to either give less bandwidth to users, or you have to deny the services, because it is not actually, we should not say low bandwidth, we should say that less efficient allocation. If it would have been efficient allocation, then we would have automatically high bandwidth, right? The problem is not low bandwidth, problem is the allocation is not efficient. Okay, so as the number of users increases, the efficiency or um, right, your efficiency is not that much, right? And uh, one more issue we are having, that we will see what is that. So let us consider T is mean time delay, that the time that is taken uh, in service. Rather, suppose I am a station, right? I have certain frames that are arriving to me, and I have to send them on the channel, right? So okay, this will I have to transmit them, right? Or when they come, they can come from other machine, or I am generating the frames, that is all right. Suppose I am generating certain frames, right? And I am, after generating, I have to send them on the channel. So what is the mean time that my frame has to wait before getting serviced in the channel? That means before getting transmitted in the channel, right? So that is known as mean time delay T. What is that? That once my frame is generated, after that it gets serviced in the channel, that it gets transmitted in the channel, and before that it has to wait some time. Why? Because possibly I am having lesser bandwidth because of FDM, or if I am having, it is not my turn, possibly it in TDM, so I have to wait for some time. So that is T. Okay, assume that frame is generated at the rate lambda, and channel can carry C bits per second. C bits BPS, C bits per second. So in my channel at max I can send C bits per second. Okay, and what is the next is each frame, or what is the length of the frame, how many bits I am generating a frame of 1 by mu bits. Okay, so what is mu? Mu is how many bits per frame, how many bits are there, 1 by mu, that many bits per frame. Okay, and what is C? That how many bits in my channel can be carried out. So can you tell me how many frames can be carried out by my channel? C bits can be carried out per second, and 1 by mu bits are per frame. So how many bits per second can be carried by my channel? C bits can be carried per second. 1 by mu bits per frame are there. So how many frames per second can be carried? Are you clear with the question? Okay. What in my channel, how many bits I can send per second? They are C bits. So in 1 second, I can send C bits. Okay. I can send C bits per second. Okay. And what is given in one frame? How many bits I am having? 1 by mu bits I am having in one frame. Okay. So how many frames I can send in 1 second? That is what my question is. 1 by mu bits I am having per frame. In one frame, will it be mu c? Okay, how you calculated it? See, how 1 second, in 1 second I have c bits to transmit, right? I can transmit c bits. So so what I have to check in one frame, if I'm having 1 by mu, so if I'm having 1 by mu frames, 1 by mu bits in, yes, I have 1 by mu bits in one frame. So in c bits, how many frame can be there? That many frames, that many bits I can transmit. So that many frames I can transmit. That is quite easy. So c divide by 1 by mu, that is mu c. So yes, it will be c by mu. Will it be c by mu or it will be mu c? C. Yes, it will be mu c. So mu c frames can be transmitted in a channel. Mu c frame can be transmitted in a channel. Okay. So lambda frames are arriving and mu c frames can be transmitted. Okay, so now we are not going to go in the much detail, but queuing theory will show that, suppose what we have assumed here, that my frames are generated at the rate lambda. On an average, lambda frames per second is generated, and current what that generation of this frame will follow the Poisson's arrival, Poisson's distribution, that at this, in this second how many frames will be generated, that will follow the Poisson's distribution. And on an average in that Poisson's distribution, my mean will be lambda frames per second. You can understand this distribution, right? So Poisson's distribution will be like this. And what is the meaning of this? That it is a possibility that on this second particular frames are generated, is it can be given by this curve, but on an average it will be lambda frames per second. So what is the instantaneous probability of generating the frames on this second will be different, but on an average it will be lambda. Poisson's distribution will be followed, not uniform, not normalized, that is Gaussian distribution, but Poisson's distribution will be followed for them. And what is the arrival rate? What is the generation rate? This lambda. And what is assumed? These are the assumed things. So how many frames can be serviced? Is mu c frame can be serviced. Lambda frames are arriving, and then queuing theory says that mean time delay that my frame has to wait here, in general, is given by 1 by mu c minus lambda. This is general. It is not related to. So don't you have you ever haven't you seen this uniform distribution or anything earlier? Have you gone through any distribution earlier? Do you understand Poisson's distribution? Uniform Gaussian is known. So according to that, we have a Poisson. So see, if it is a Gaussian, it will look like this. It will have its own equation and all, right? What is the meaning of that? What is the probability that suppose I am saying that this is okay, so this is what is the probability that this is the mean value? Suppose this is the mean value, and this is my, and this is the probability value, and this is my frames per second, right? Frames per second that is generated. This is frames per second, generated frames per second. So on this second, in this second, the number of frames generated will be number of frames generated will be, say, 1. This is 1, suppose, and this is, say, lambda, and suppose this is, say, k. So probability that in this second 1 frame will be generated is given by this. Probability that on this second k frames will be generated will be given by this. And this curve is nothing but that is, suppose it is a Gaussian curve, then it will be this type of curve will be followed, right? And what is the meaning here? Suppose this is this one is maximum here, and if you know that this will give you the mean value. So what is the meaning of this? That that in this second lambda frames will be generated is having the maximum probability, right? So I mean, maximum on in general, almost every second there will be lambda frame generated. Okay, and if you will take the mean of this entire curve, it will be almost lambda, right? So what is the meaning of that? Meaning of that meaning of this if this distribution is, it will give you that at this second, what will be the, what is the possibility that that many number of frame is generated, right? So so that is this is the distribution. Now this was a Gaussian, but if I'm going for the Poisson, it is a different shape. The Poisson has this type of distribution, and here the lambda will come, that is mean value. Again it will be the same thing, that what is the probability that this many frames will be generated this second is given by this, and what is the probability that this many frames will be generated, it will be given by this, right? So Poisson's distribution, it is that how many cars will come at the petrol pump, that type of questions I think you have gone through in the DM, right? And that will follow the Gaussian distribution. So how many things will arrive at this moment, and probability of that is given by the particular distribution, and that is what is Poisson's distribution with lambda mean. So whatever the probability at the current moment, but on an average on the last scale, if you will see, it will be lambda. Is it clear to you now? Okay. So see, this is what is given by 1 by mu c minus lambda. Okay. Now, uh, that is this thing we are not going to follow, but on an, you can understand, it is giving you that how this delay can be generated. That the delay is what, that how much I have to wait here. So it will depend on how many I can send and how many are generated. It will depend on the difference of them, right? So that is what you can see, how many can be transmitted minus how many are generated, and difference of that is related with this delay, that how much my frame has to wait here. But of course we are not going to prove it, it is from the queuing theory, so we are not going to prove it. Where I am interested, I am not interested in that part. Where I am interested in, this was a general case, right? But what will happen here whenever it is now this channel is shared, that what was the channel characteristic? Channel characteristic was, it can carry c bits per second, right? It can carry c bits per second. And what was another characteristic of this interface? Interface was generating lambda frames per this input was lambda, and the c bit was the capacity here, right? Now what will happen, now it is shared by many users. Now this interface, because it is now shared medium, it is shared by many users, but input should remain same. Input arrival, we are using the same distribution, input will remain same, right? So how much it is permitted to how many frames each user will generate. Now suppose n users we are having, right? And I have to keep my input same, because I want to see, I want to compare it with how much delay is introduced because of sharing, right? Earlier this was the delay if it was no sharing and only one user was there, and it was generating lambda frames, right? Now what will happen, how much is permitted to how much each user can generate, it will be lambda by n. So n user in general will generate lambda by n into n, that is lambda is totally generated, right? And what will be the capacity that will be given to each user, because it is shared. Suppose it is FDM, so how much will be the capacity will be given to each user by channel, how much will be the capacity, it is shared, so each user will get equal bits per second. And how much it will be, how much capacity to each user will be given? Total capacity of the channel is c bits per second. It has to be shared among n users, so how much capacity should be given to each user? Yes, it will be c by n. So now for each user, in generation rate is lambda by n, and output rate is c by n. So c by n is the output rate, capacity is not c but it is c by n, and generation rate is not lambda, it is lambda by n. And hence if you will see, the delay is increased by n times. Okay, so in short, what is the conclusion here? See, whenever you are having more users, right? ultimately, if you don't do this is fine, this is mathematically you can show, but if think of like, see, if you would have got the entire bandwidth, then you can transmit more and more bits per second, right? But suppose you have lesser bandwidth, suppose you had 4 kilo instead of 12 kilohertz, you had 4 kilohertz, that means you can transmit less number of bits per second, right? And hence you have to, your delay will increase. Suppose it is even smaller, if your earlier you were having 12 kilohertz, now you are having 4 kilohertz bandwidth. Why? Because there were 3 users, that means totally bandwidth you could have get divided by 3, because of n, you were having that issue, right? And delay was increased 3 times, because now you, instead of sending instead of sending up to, at the rate 12 kilohertz, you can send up to 4 kilohertz only. Nirav, Nirav, any doubt, Nirav? Okay, so are you getting the point? Like, if because you have less bandwidth, less capacity, and definitely the delay is going to increase, and it will be directly proportional to the number of users. Can you understand that point logically? Can you understand the point logically? Okay, but still we are not interested in the static allocation, as user it is shared, and we don't want to go with the static allocation, so we should go with the dynamic allocation, right? So so in that dynamic allocation, we need to understand again some terminology. First of all, we have to go with the station model. What is station model? It is what is station model? It is like now I have multiple stations. As I told you, multiple machines are there. I will call them terminal, right? And assuming that there are n terminals, n stations are there, right? They are having two modes of operation. One is writing, another is transmitting, right? Writing is what they are preparing a frame. What is transmitting? When they are sending a frame. Here, what we have assumed for the simplicity, when they are transmitting a frame, they are not generating a frame. And when they are transmitting, they are just simply transmitting. They are not writing. And when they are writing, they are not transmitting. I mean, both operations will not go simultaneously. Either they are writing or they are transmitting. Okay. Of course, there will be a single channel. Otherwise, why we are learning lot many things? Collision assumption, that collision may take place and we want to avoid it, right? So there will be a collision, and we have discussed what is collision. The collision concept we have already discussed. Yes, this is important. Just continuous time and slotted time. So what is continuous time? That as soon as I have data, I can send, right? That is continuous time. I will not see that whether any time I can generate. I can use the time in continuous mode, right? And what is slotted time? If I have a data, then I have to wait for my next slot. Not necessarily it is allocated to me, but the next slot. Like I can send at 12 hour, then I can send at 12:15, then I can send at so I have a slot of 12 to 12:15. So whenever the data is generated from 12 to 12:15, whether it is at 12:01 or it will be at 12:05 or it will be at 12:10, but I can send at 12:15 only, right? Once I have data, I have transmitted at 12:15, then I have to wait for 12:30. So there is a slot of 12:15 to 30. I cannot send data if my data is ready at 12:17. I have to wait for 12:30. So that is slotted time. I have to wait for the next slot when we are permitted to send. Is it clear? Slotted time, continuous time. Continuous time is what if data is ready at 12:16, I can send it immediately. Is it clear to you? Slotted and continuous time. Is it clear? See why I'm asking intermediately, so that because these things are at the end they are going to come together. So at that time it should not create any kind of confusion. Are you clear with the continuous time and slotted time? Okay, great. What about carrier sense and no carrier sense? Carrier sense is what? Uh, Carrier sense is you will listen the channel before transmitting, right? And no carrier listen the channel means what? You will check the voltage of your line, that like kind of thing, right? So you will listen your channel before transmitting, and like whenever it is like, whenever you will start transmitting, you will utilize your channel, you will check, is there any voltage on the line, what is the meaning if there any, that means someone is transmitting. So I should not transmit, because anyway I'm going to lose my data and the other one's data as well. So better we should not transmit. That is carrier sense, and it is possible that we are not doing any carrier sense, so it is no carrier sense. So before transmitting, I'm not sensing. So that is what no carrier sense. So now we are going for the dynamic allocation of channel, and first of all, and for most common one is protocol is pure aloha, right? So history of this aloha is given in the book. What was how it was developed, and some brief history is given. A small 2-3 line paragraph is there. Of course, you have to read it, that in which laboratory, at which year it was started. But let us learn that what exactly the scheme is. Pure aloha is the simplest one. Is like, as soon as you have data, you just transmit. Okay, so now what is happening? Suppose this is my interface, and this is my time axis. Okay, this is time. Here I'm assuming that at this is time 0. I'm assuming my time is 0, then it will become 1, then it will become 2. It is continuous time. Okay, so it is not like slotted, though I've drawn the slots. Okay, so now suppose someone has the frame. Suppose I have I have machines A, B, and C. Three are having they are sharing the channel, right? That means how it looks like. This situation is like this: A, B, and C. Right now, assume that this has frame. Assume that frame time. Frame time is 1 microsecond or 1 microsecond. Let us keep it as 1 microsecond. Assume that the frame time is 1 micro. What is the meaning of frame time? What do you understand when I say frame time? It is a new what you can say terminology. What is frame time? A time taken to transmit a frame. Frame time is the time taken to transmit a frame. From the start of the frame to end of the frame, if I transmit them on the channel, it will take 1 microsecond. Frame time is time taken to transmit a frame. And this is also assumed that it is in 1 microsecond. Okay, so now suppose that this A has a frame generated at 1.2 second, at 1.2 microsecond, it has frame to transmit. Because it is using pure aloha, as soon as it is ready, you just transmit. So when it will start transmitting, 1.2 microsecond, the frame was ready to generate. So when it will start transmitting, A will start transmitting when? At which time it will start transmitting? At 1.2 microsecond. At 1.2 microsecond, it will start transmitting. And what is the frame time? It is 1 microsecond. So it will start transmitting at 1.2 microsecond. It will continue transmitting up to which time? It will, yes, it will be 2.2. It will from 2.2. So 1.1 to 2.2, it will keep sending. What is the meaning of this? When I write like this, what is the meaning here? On this channel, from 1.1, 1.2 to 2.2, the data will be of A. Is that the meaning? That is the meaning, right? So this line is occupied for 2.2. Now, now this has data to transmit at say 2.1. This has data to transmit at 2.1. Okay, so what will happen now? So can it transmit? Can it transmit? It should not, but can it transmit? Yes, it can transmit. What is aloha? As soon as you are ready, you have to transmit, right? So it is ready to transmit at 2.1. So it is going to start its communication at 2.1, and here it will stop at 3.1, because again here it is assumed that frame time is 1 microsecond. So this is what your here the collision happened. In this duration, collision happened. That because this was just about to end and this just started, but the garbage is going to keep this is going to happen. This the data, the voltage levels are going to get combined. And which frame is destroyed? A's frame or B's frame or both? Which frame is destroyed? Whose frame is destroyed? A's frame, B's frame, or both? Both will get destroyed, right? Both will get destroyed. True, both will get destroyed. So so that is what is shown here, that whenever, see here, if you will see, if it exactly completes and the next one starts, then is no collision. If this completes and new starts, there is no collision. But here also there is no collision. But here if you will see, there will be a collision. So can you tell me, this aloha will create problem when the load is high or when load is low? Load is high means what? All the stations have lot many things to transmit, and low load is what? That all the stations are easy. They are not having much load to transmit. So aloha is problematic in high load or low load? Yes, in high load. In high load, it is going to create the trouble. So this is aloha scheme, right? Now we have to understand some mathematics behind it. So let us understand few things before we go to that one. So what is aloha? Then when user have data, it can they can transmit. What is aloha scheme? What is aloha scheme? As soon as they have data, they can transmit. But after transmitting in aloha, channel is A is going to listen the channel, and it is going to see whether the collision has happened or not. Okay, it will come to know by listening the channel. By listening the channel, it will sense that whether the collision has happened or not. And if collision has happened, then it will wait for the random amount of time, and then it will retransmit. Suppose now A and B were collided, both will come to know, okay, our frames are collided, so they have to retransmit. When the collision happened, that means both frames are lost. So once the frames are lost, they have to retransmit it, right? So uh, now they will wait for the random amount of time. The time, why they should not wait for the fixed amount of time? Can they wait for the fixed amount of time, or it is required to be a random amount? Can it be a fixed amount of time? Yes, if it is, it has to be random amount, because again, if they are will wait for the 2 seconds, and again both will wait for 2 seconds, again then collision is going to happen. One has to wait for 2 seconds, another has to wait for 5 seconds, right? It has to be random, then and only then collision in future might be avoided, right? So they will wait for the random amount of time and then will resend. And while you are listening the channel, if it is not possible you for the listening the channel, like if you cannot detect the channel for the collision, then you need some kind of acknowledgement. Someone has to tell you that acknowledgement that your frames were not reached properly. So you can, if your machine is weak in listening, then you can use acknowledgements for detecting the collisions. Rather, I should say, be aware about the collisions. Okay, and here we have one more term, that is contention systems. What is contention systems? Um, and see here we are, see here machine A, B, C are competing for the channel. They are competing for the getting allocation, and that's why they are known as contention systems. Contention is what? Competition. Okay, so we can say that multiple users are desperate to take the channel, and hence the conflicts are happening, and these channels are known as contention systems. These machines are known as contention systems. Okay, so as I told you, the user is always in one of two states: either it is typing or it is waiting. Or that means when it is in waiting, what is the meaning of that? It is transmitting and waiting for the either successful transmission, or it is waiting for collision to happen so that it can take the next decision, right? So at the same time, it cannot do two things. When it is typing, it cannot transmit, and when it is waiting, it cannot type. It is blocked. For the simplicity, we have taken so, right? What we have further assumed, that it is infinite population of the user. That means there are so many users. So why we are assuming so? So see, why we are assuming that so we are having so many users. So when suppose we are having 1,000 or more users, few of them are typing right now, and after typing they will transmit, right? So when they are transmitting, they cannot write. right? So what will happen, suppose I'm having very limited users, so possibly there is no one who has next data to generate, so possibly average amount of frames that are generated per second in my system, which is assumed n, may reduce. What I've assumed here, that n frames per second are generated in my system. For mathematical purpose, what I assumed, that n frames are generated, right? So every second there will be n frame which are generated. Okay, but suppose I have 10 users only, and all out of them, many of them were typing earlier, now they are in block state because they are waiting, they cannot type, right? So this n will not be maintained, right? N number of frames might not be generated. So that's why what I assume, I have infinite users, that's why n will be maintained. So on an average, n frames per second will be generated. Okay, so and if you don't want to go with that, na, what you can think, if you want to go with real time, so what will happen, that when it is transmitting at that time, it can generate as well, then also n will be maintained. Suppose infinite users are not there, but users are not, right now we are having powerful users, right? So if they are transmitting, they can generate at the same time. So again, the definition will be correct here, that n frames per second will be generated. Okay, okay, so now what we have assumed, that n every time n frames per second is every frame n times per frame time, per second, not per second but per frame time. In one frame time, n frames are generated. Okay, now that is, here it was 1 microsecond. In 1 microsecond, n frames are generated. Okay, fine. Now the next case is G. This is actual this n was n frames in one frame time generated. Okay, so in every 1 microsecond, n frames are generated, new frames generated, and G is what? In one frame time, this many frames are transmitted in the channel. So are they same? The number of frames generated and the number of frames transmitted, are they same? What can, is G greater than or equal to or less than n? What is the relation between G and n? N is what? See here, what simple things are there. Aloha is very simple, right? As soon as I have data, I have to transmit, right? Let me tell you. Let me tell you. G, all three answers are there here. All three answers, or maybe multiple combinations might come. What is my question to you? See, Aloha, don't we will go with the mathematics, but let us keep it very simple. What is that? I have n users, right? Suppose I have not n users. Suppose I am having small n users. Suppose I am having small n users. So I am having a common wire in that I have n users with me, and they are generating n frames, capital M frames per frame time. Okay, so in one frame time, how many frames are generated? So there are n frames are generated per frame time. Okay, so in one frame time, how many frames? So what should be the value of n? Let me know. What do you think? What should be the value of n? Should it be greater than 1, or it should be equal to 1, or it should be less than 1? In one frame time, how many frames should be generated? What is the meaning of this? See, in one frame time, how many frames should be generated? This is one frame time. Suppose I take any random one frame time, how many frames should be available here? How many frames should be generated rather? N is in one frame time, how many frames are generated? Uh, N should be greater than or equal to 0. Okay. N should be equal to 1. That is, so in one frame time, if only one frame time, if it is only one frame is generated, then it is good, right? That I agree with your case. Like in one frame time, if only one is done, then it is good. But we will prove it soon that if n is less than 1, then it is even better. What is the meaning of that? Not in one frame time, but that is suppose in two frame time only one frame is generated, so that is even better. Like in the large span, if only one frame is generated, then even better. That is in two frame time only one frame is generated. That is in one frame time half frame is generated. Are you getting the point? In two frame time, suppose I say only one frame is generated, and then in two frame time only half frame is generated. Suppose in every 2 microsecond, one frame gets generated. So in every 1 microsecond, how many frames are generated? So it will be zero point 0.5, right? So logically think what do we want to say here? That what we want to say here, that when I generate, or when very low load is that, is it every 2 microsecond only one frame is getting generated. If it is three or more, then even lesser load is there, right? So what is the case, like n is what, that in one frame time how many frames are there? You might think that at n is equal to 1, if every frame time if one frame is generated, that it is good. I agree with that. I agree with your understanding, but we will prove soon that if n is less than 1, that is even better than that. Okay, so that is fine. I hope you understood. So what is the case, that every machine is generating n frames, right? In per frame time duration, n frames, not every, but in general totally n frames are getting generated on this line in one frame time. Okay, now what is g? G is number of frames on this channel in one frame time, or number of frames transmitted on this channel in one frame time. So number of frames generated are number of frames transmitted, or when we are transmitting, we are having which are the frames that we are transmitting over this channel? We are transmitting the new frames that are generated plus the ones that they were collided, right? So on this channel, this station might transmit a new frame generated, or it might transmit the collided frame. So what will be g? G is actually the new frames plus the collided frames. So average number of frames per frame time that are on the channel might include the new generated frame, or might include the collided frame that are transmitted again. Is it clear to you? So what is the relation between G and N? Is G smaller than N, or is G greater than N, or is G equal to N? Yes, G is greater than equal to N. It is greater than equal to N. When it will be equal, Prince? It is greater is for sure. Why? Because newly generated plus the one which were collided, that will be the one, right? What about when it will be equal? N is equal to 1. uh, no collision. Yes, Prince. It will not be like when n is 1, at that time collision will not be that. It is your wrong perception. Prince, I'm going to clear that one. When n is equal to 1, at that time there is no collision. That is a wrong perception. But I agree with Jenny and your perception, I mean your idea even, that is that when there will be no collision, that means only no retransmission, and hence there will be only new generated frame that will be transmitted. Okay, so I agree with that. When there will be no collision, at the time G and N will be same. Otherwise, G will be greater than N. Now, next question arises that what should be the value of G? How many frames per frame time we should transmit? So you will say it is very simple. We know that. What is that? That let us think of, like what I should have is, whenever I have this is my transmission. So suppose this is one frame time. Assume that this is one frame time, and this is another frame time. This is one. Okay. Now, suppose someone has transmitted here, right? Okay, and I have transmission at this moment, right? So what will happen? So definitely collision is going to take place, right? I can tell you, like suppose see, collision will take place. Suppose I have data to transmit, right? Suppose I have data to transmit, and What and suppose I have data to transmit, and someone already has transmitted. At that time the collision will take place. Already something is in the channel and I start transmission, then collision is going to take place. Yes or no? So for this channel for suppose okay, and can I say suppose this is not there, suppose it is. So see, when the collision can take place, two situations are there when the collision take place. When I start transmission, suppose I start transmission at this moment, before my before before me someone should not transmit, and when I transmit at that time also someone should not transmit. If someone has already started transmission over this time, I will collide with them here, right? And suppose this is not there, and I have started transmission here, and someone will start transmission over here, then also I'm going to collide with them. Are you getting the point? Like here, that someone has started, so, and if I will start, then I'm going to collide. So, and whenever I'm transmitting and someone will start somewhere here, then also I'm going to collide. So when there should not be any frame. So if someone start is before me, they should start at this moment. They should not start here. They should not start here. They should not start here. So they should, when they should start, when they should not start, one frame time before me. They should not start. If they want to start, they should start here. Then what will happen? It will get completed here. Then I will not get collide. But even one microsecond, one picosecond after that also, this is going to collide with me. Is it clear or not? So one frame time before my transmission and during my transmission, that is also one frame time. There should not be any frame. Are you clear with the case? Before one frame time of my transmission and during my transmission, there should not be any frame. Are you clear with the point? Okay. So how many frame time there should not be any frame? For how much time there should not be any frame? For how much time there should not be any frame? I mean, other than mine, of course, other than mine. This is one frame time. This is another frame time. There should be two frame time. So this is known as vulnerable time. What is vulnerable time? So that in two frame time, if there is only one frame, suppose this was not there and this is not there, so in two frame time there will be only one frame. So definitely it will reach to the destination without any issue. Okay, so that is known as vulnerable time. So in two frame time, if I am having only one frame to transmit, um, then it is known as what you can say, it is safe to reach to the end. Okay, so now in the laboratory session we are going to complete this mathematical part, right? And we will complete the aloha, slotted aloha as well, and we will take examples of them, and then we will go for the experiment. So in the laboratory today we will continue from this portion. Okay, we will complete up to slotted aloha and related examples, gate examples, very useful ones, and then we will start our laboratory part. Is it clear? Are you clear with up to this point? Are you clear up to this level? Any doubt up to so far? Any doubt? Okay, so I think you don't have doubt, so you may leave. In the laboratory we will continue with this.